So good afternoon to all. Today we are going to start in continuation with what we have left in the last class. That is, we will be talking about the M-derived filters. Now, what we have so far covered, let me revise you. Okay. So basically, we were talking about the M-derived filter fundamentals, and then we have talked about the low pass filter, M-derived low pass filter. So what we have covered so far, let me go through quickly. So I have given you that now the fundamental prototype constant K filter will be changed. That is changed in the sense that there is a impedance values will be changed. That is now, let us take example of symmetrical T network. Then it will be not Z1, it will become MZ1, and therefore the two half section will become MZ1 by 2 and MZ1 by 2. And because of this changing of the Z1, the Z2 will also change. And we have gone through its mathematics also by using the principle that the characteristic impedance in the prototype section as well as in the M derived section will remain same. So accordingly, we got the T section will be modified as follows. The T section will be modified as follows. That is the series arm will be MZ1 by 2, MZ1 by 2, and the shunt arm will be consisting of two components. One will be Z2 by M, another will be Z1 1 minus M square upon 4M. Clear. Then we have also talked about the pi section. We have derived the same thing for the pi section also, and we found that in this case the shunt arm will be twice Z2 by M, twice Z2 M. By shunt arm will be changed. Okay, and it will consist of again two components which will be connected in parallel. The series arm will consist of two components connected in parallel. One is MZ1 and another is 4M upon 1 minus M squared Z2. Okay, then we have gone through the derivation of M derived low pass filter, where we have used the concept of the frequency of attenuation, frequency of infinite attenuation F infinity. Okay, it is being selected in a low pass filter so that it is greater than the cutoff frequency. Means it should be near about it. Not greater means doesn't mean that it should be at a very infinite place, because had it been infinite, then the M will be equal to your uh, 1. So we are choosing f infinite, and for that purpose, after choosing f infinite, we find out the value of m. The m comes out to be under root 1 minus fc upon f infinity whole square. Now from this it is very clear that the f will have a value less than 1 or between 0 to 1. Okay, so when it will be 1, when your fc will become equal to f infinite. Okay, so then it will become 1 minus 1 is equal to 0. Okay, and then m is equal to 0. Okay, and when we will get the value 1, okay, when the f infinite will be very at large distance, that it will be very infinity. So 1 minus fc upon infinity will give you 1 minus 0, and therefore under root 1 will you get 1. So therefore it lies between 0 to 1. Either it should be very near or it should be very far away. Okay, so far away is not being desirable. It should be always very near to the cutoff frequency. Okay, so with this much of background, then we have also talked about the attenuation constant. We have also talked about the phase shift. Okay, then this was the slide where today I will talk about you in what this slide is representing. This slide is representing the variation of the attenuation and the variation of the phase shift with respect to the frequency, and also the variation of the character impedance both in pi section and T section of M derived low pass filter. So let us first of all talk about the characteristic impedance. From it is clear that the ZO pi in the case of the pass band, because this is the pass band, okay, existing from 0 to fc. Okay, so we find that the again it is of the similar nature as that of the low pass constant K filter. Okay, now we'll talk about the so-called attenuation alpha. as you can see that in the pass band, okay, the attenuation is 0, that is desirable. But in the stop band, previously it was goes on increasing and it was reaching the high value at a very, very high frequency. But now we have selected the frequency of infinite attenuation approximately near to the cutoff frequency. So no doubt still the problem persists, but we have minimized it. We have minimized it that very soon. Now it depends upon how much you choose f infinity. If you choose f infinity in close proximity with the cutoff frequency, then you will reach the infinite attenuation or a high value of the attenuation at a very low values. Okay, so all things depends upon the design engineer how he choose the f infinity. It should not be below cutoff frequency. It is always greater than cutoff frequency, and you can see that very soon it reaches to a very high value. Okay, so and thus overcome the disadvantage. Okay, no doubt this disadvantage is still there in this band from fc to infinity. It is not rising sharply, but very soon in a millisecond or a microsecond it reaches to the infinite value. Okay, similarly the phase shift property will remain as it is. Okay, that is in the pass band you will have a phase shift which is following the sine inverse curve, while in the stop band it will always remain pi. Okay, so only change is there in this, the attenuation is there due to the use of this m ratio. Okay, that is why they are not the m derived filters. So now let's come to the numerical. So be cautious regarding the numerical. So if you will do like this, that you will remember the m derived filter formula but does not remember the formula of constant decay filter, then you are in misnomer. Okay, because all the m derived filters are basically using the formula of constant decay filter only. Is it clear? So you have to remember all the formulas of the constant decay filters. Okay, or you must know their derivation. Now let us take a numerical. The numerical is design an m derived t and pi network. Okay, so both network has been asked for a low pass filter with nominal characteristic impedance or load impedance or terminal impedance is 900 ohm, and the cutoff frequency is given 0.9 kilohertz, that is 900 hertz. And also the infinite attenuation frequency 1 kilohertz. Now you can compare that the two frequencies are very near about to each other. It is 0.9 kilohertz, 900 hertz, while it is 1000 hertz. Okay, so it is very near about it. So very soon you will get the infinite attenuation in the stop, a very large attenuation in the stop band. Okay, so let us perform. First of all, what is given that I have marked here, R naught is being given to you. Okay, you can see that R naught is nothing but 900 ohm. Then you have been given the cutoff frequency 0.9 kilohertz and the infinite frequency 1000 hertz or 1 kilohertz. Okay, so these are being given to you, and now let's find out the two sections, the two T and pi network of this low pass filter. Okay, so the first step will be to find out the ratio m. The m we have to find out, and for that purpose we have already derived that m is nothing but under root 1 minus fc upon f infinite square. Now these two fc and f infinite have been given to you. We will just substitute the value as you can see in the numerical. Okay, I have placed the value of fc is equal to how much? 0.9 and f infinity is equal to 1. Now mind it, be cautious regarding the units. Okay, if you place in the kilohertz, then both should be placed in the kilohertz. If you place one of them as a hertz, then the other one, that is f infinite frequency, should be also in hertz. So if I place 900 upon 1000, then it should be like this, and if I place in kilohertz, then it should be 0.9 upon 1. When you solve it with the help of the calculator, you will find that m comes out to 0.436. Okay, so with this much of the m, now we'll find out the value of the L and C. Now once again, I was emphasizing that you should know the formula for the prototype, that is the constant K filters parameter values. How you find out it? You know that in low pass constant K filter, the values of L is given as R naught upon pi fc, which we have already derived it and also understood it, that how it is being derived. So I just substitute the value, and by substituting the value of R naught is equal to 900, pi is equal to 3.1416, and cutoff frequency value 0.9 into 10 raised to the power 3. Mind it, do convert it into all into hertz and all this. Then we will get a value of inductor as a 318.3 millihenry as shown on the slides. Now, similarly, we find out the value of C as per our previous knowledge. We know that C for a prototype filter or constant K filter is given as 1 upon pi R naught FC. I just substituting the value pi 3.1416, R naught 900 and FC is 0.9 into 10 raised to power 3, or simply I can write 900 also. When I solve it, I will get the value of capacitance in microfarad as 0.393. तो कुल मिला के मैं आपको ये बताना चाहता हूं कि यदि आपको एम डिराइव फिल्टर्स के न्यूमेरिकल्स करने हैं तो आपको कांस्टेंट के फिल्टर के सारे फॉर्मूले आपको ध्यान में होने चाहिए, क्योंकि हम उनका प्रयोग वापस इस प्रकार यहीं पे करेंगे। तो एक जो समझदार एग्जामिनर होगा वो हमेशा आपको एम डिराइव फिल्टर का क्वेश्चन देगा, ताकि आपको कांस्टेंट के फिल्टर के भी कॉन्सेप्ट क्लियर हो जाए कि आपको उसके फॉर्मूले याद है कि नहीं है, उसके कॉन्सेप्ट मालूम है कि नहीं। अब इन दोनों की सहायता से, जैसे कि मैंने एल का जो फॉर्मूला है वो कांस्टेंट के का लिखा है, सी का ये कांस्टेंट के लो पास फिल्टर का है, और हमारे पास ये दो वैल्यू आई। अब हम इन दो वैल्यू का यूज करेंगे एम डिराइव फिल्टर सेक्शन के डिजाइन में। ठीक है, हमें मालूम था कि एम डिराइव फिल्टर में जो कंपोनेंट्स होते हैं वो क्या क्या होते हैं। इज इट क्लियर? यू नो दिस ऑल दिस फैक्ट? So I have calculated MC. So what is MC? MC is nothing. M we have already find out. We just multiply with the value of the C 0. It comes out to be 0.171 microfarad. Then we have to find out MC by 2. Okay, we just half it, we will get 0.0855 microfarad. ठीक है, ये हम सारा मैथमेटिक्स कर रहे हैं जो हमें कंपोनेंट की वैल्यू चाहिए। ठीक है, अब हमें चाहिए 1 माइनस एम स्क्वायर 4m, क्योंकि आप देख सकते हैं जो टी सेक्शन है, मैं आपको एक बार फिर दिखा देता हूं टी सेक्शन। इज इट क्लियर? टी सेक्शन है, टी सेक्शन में हमें देखिए क्या चाहिए, एक तो ml बाई 2 चाहिए, वो भी हम करेंगे। एक हमें एम सी और 1 माइनस एम स्क्वायर अपॉन 4m चाहिए, ये वैल्यू चाहिए। तो ये वैल्यू मैंने कैलकुलेट की है, आप देखिए न्यूमेरिकल में। ठीक है, 1 माइनस एम स्क्वायर अपॉन 4 है। जो एम सी बाई 2 है वो हमें आगे चाहिएगा। इज इट क्लियर? पहले निकाल दिया है, कोई बात नहीं, हम पहले टी सेक्शन की बात करें। टी सेक्शन में एक तो हमें चाहिए एम एल बाई 2, तो एम एल बाई 2 यहाँ पे आपके निकाला हुआ है मैंने। इज इट क्लियर? आप देख सकते हैं एम एल कितना होगा, एल को मल्टीप्लाई कर दीजिए एम से, जो हमने अभी निकाला 0.4 समथिंग। ठीक है, जब हम प्लेस करूंगा वैल्यू तो मेरे पास आएगी 138.8 मिली हेनरी। ठीक है, और एम एल बाई 2 कितना हो जाएगा, 69.4 मिली हेनरी। तो हमारे दो एल हाफ सेक्शन मिल गए हैं जिनकी वैल्यू कितनी है, 69.4 मिली हेनरी। यहाँ देखिए इंडक्टर है और यहाँ पे भी 69.4 मिली हेनरी। अब मुझे शंट आर्म निकालनी है। सीरीज आर्म का खाता क्लियर हो चुका है। शंट आर्म में मेरे दो कंपोनेंट्स होते हैं और दोनों सीरीज में होते हैं। एक क्या होता है, इंडक्टर होता है, और एक क्या होता है, मेरा कैपेसिटर होता है। जो इंडक्टर की वैल्यू है वो कितनी होती है, 1 माइनस एम स्क्वायर अपॉन 4m, 1 माइनस एम स्क्वायर अपॉन 4m। ठीक है, तो ये मैंने यहाँ पर 1 माइनस एम स्क्वायर अपॉन 4m मल्टीप्लाई बाय एल कर दिया, तो मेरे पास आया 147.8 मिली हेनरी। 147.8 मिली हेनरी, ये मैंने यहाँ रख दिया। और जो दूसरा शंट आर्म में जो कंपोनेंट होता है, सीरीज में कनेक्टेड होता है, वो होता है कैपेसिटर। और इस कैपेसिटर की वैल्यू कितनी होती है, ठीक है, अगर आप वापस रिटर्न बैक करें तो आप पाएंगे, बार बार इसको आप मनन जब तक नहीं करेंगे तब तक ये फॉर्मूला, यहाँ कितनी थी वैल्यू एम सी। इज इट क्लियर? वी हैव ऑलरेडी कैलकुलेटेड एम सी। ठीक है, ये एम सी हमने यहाँ पर कैलकुलेट कर लिया था, कितना आया था, 0.171 माइक्रो फैराड। ठीक है, तो यहाँ पे हमने लिख दिया इसको 0.17 माइक्रो फैराड। ठीक है, तो आई थिंक सो इट इज वेरी क्लियर। इज इट क्लियर हाउ टू फाइंड आउट द एम डिराइव low pass filter? Is there any problem? You just can write down in the chat box that if there is any problem in the understanding that अगर इसको समझने में कोई दिक्कत है आप चैट बॉक्स में लिख सकते हैं, अदरवाइज वी विल प्रोसीड फर्दर। No. So no reply has been obtained from you. With this, I assume that you understand everything. Now, how my pi section will look like? Again, pi section. So you have to go through the. I will show you the diagram of the pi section. Now, pi section is very clear. There are twice Z2 by 2 is there in shunt arm, which will become MC by 2. Mind it, twice Z2 will become, twice Z2 by M will become MC by 2. Is it clear? And what other values? We will have a ML and 1 minus M square 4M. So I am using here the same concept twice. So MC by 2, okay, we have already calculated, it comes out to be 0.085 microfarad. Is it clear? And what about this, the series arm? It again consists of the two components, okay, inductor and capacitor, which are connected in parallel. Okay, the inductor value is given as ML, so M multiplied by L, 138.8 millihenry, and this capacitor, okay, this which is connected in parallel with the inductor, is given value 1 minus M square upon 4M into C, which come out to be 0.182 microfarad. Okay, so you just have to place the value. What conclusion you are finding? That be cautious regarding the values. So first of all, calculate M, calculate L, calculate C. Once you have calculated, now you can put forward both M and C values according to the T section or the pi sections parametric values. ओके, सो आपको ये ध्यान में होना चाहिए कि टी में क्या दिखता है. टी में हम ml by 2 होते हैं सीरीज सेक्शन में, और वहां पर शंट आर्म में सीरीज में दो कंपोनेंट लगे होते हैं, जिसमें एक की वैल्यू ml by 2 होती है और एक की कुछ 1 माइनस एम स्क्वायर, जो मैं पहले आपको दिखा चुका हूं. 1 माइनस एम स्क्वायर 4 एम पर एल होता है, सॉरी, और जो सी की वैल्यू होती है वो होती है एम सी. इज इट क्लियर? तो ये सारी चीजें आपको याद रखनी है. पाई में भी इसी प्रकार याद रखना है कि जो शंट आर्म होती है, ठीक है, वो एम सी बाई 2 होती है, और जो शंट सीरीज आर्म होती है वो दो पैरेलल कंपोनेंट से बनती है. पहला एम एल होता है और दूसरा 1 माइनस एम स्क्वायर 4 अपॉन एम सी होता है. ठीक है? सो दिस इज ऑल अबाउट द design of an M-derived low-pass filters. Our next session will be related to the M-derived high-pass filter. ठीक है, हम हाई पास फिल्टर के संदर्भ में बात करेंगे. वही प्रोसीजर वही सेम है. ठीक है, हल्का सा चेंज आएगा. चेंज किस में आएगा? एम के रेशियो में. ठीक है, और बाकी एल और सी की वही वैल्यूज है जो हमने हाई पास फिल्टर के लिए, हाई पास कांस्टेंट के फिल्टर के लिए ली थी. एग्जैक्टली. तो मैं बार बार ये कह रहा हूं कि आपको कांस्टेंट के फिल्टर के फॉर्मूले सारे याद होने चाहिए. यहां पर हमें सिर्फ निकालने की क्या जरूरत है? एम की. और एम किससे निकालेंगे? कट ऑफ फ्रीक्वेंसी से और फ्रीक्वेंसी ऑफ इनफाइनाइट एट्यूनेशन से. इज इट क्लियर? तो आगे बढ़ते हैं हम. ठीक है, कैसा लगेगा हमारा टी सेक्शन और कैसा लगेगा हमारा पाई सेक्शन. इसमें से थोड़ा बहुत हमने कुछ, सॉरी, ये डायग्राम थोड़ा सा गलत पेस्ट हो गया है. बेसिकली आई एम सॉरी फॉर दैट. ओके, बेसिकली इट इज नॉट, दिस इज द डायग्राम ऑफ द लो पास फिल्टर. दिस इज नॉट द डायग्राम ऑफ द high pass filter. This is by mistake it has been printed here, so I will correct it, and when I will send you the notes, then I will correct it. But it is not the diagram of the, this is the diagram of the low pass filter. अब आप high pass filter क्या होगा आप खुद बता सकते हैं कि यहाँ पर क्या होता है. यहाँ पे क्या होता है? एम जेड वन होता है. एम जेड वन, और जेड वन हमारा हाई पास फिल्टर में क्या होता है? सो प्लीज फॉरगेट अबाउट दिस, आई एम जस्ट करेक्टिंग इट हियर. सो यहाँ पे हमारा होता है एम जेड वन. इज इट क्लियर? तो एम जेड वन मीन्स, और जेड वन हमारे लो पास फिल्टर, हाई पास फिल्टर में क्या होता है? ठीक है, 1 अपॉन जे ओमेगा सी. ठीक है, 1 अपॉन जे ओमेगा सी. तो यहाँ पे जो वैल्यू होगी वो ये नहीं होगी, वो कितनी होगी? सी बाय एम. और यहाँ पे भी कितनी वैल्यू होगी? सी बाय एम. Okay, so I'm just correcting the diagram. Okay, you just I will send you the corrected slide. Okay, similarly हम जब वैल्यू कैलकुलेट करेंगे, ठीक है, Z2 की, ठीक है, तो वो भी वैल्यू चेंज होगी. वो कितनी होगी? लेट मी फाइंड आउट. Is it clear? So it will be again consist of the and series arm and shunt arm. The shunt arm will consist of an two components L and C that will be connected in series. ठीक है, आपको मैं ये बता दूं तो डायग्राम में वही होगा. जैसे यहाँ पे होगा आपके एक कैपेसिटर और यहाँ पे होगा कैपेसिटर. इज इट क्लियर? और कैपेसिटर की वैल्यू मैं जैसे कैलकुलेट कर रहा हूँ, कितनी होगी? सी बाय एम, और ये वैल्यू होगी सी बाय एम. इज इट क्लियर? और यहाँ पे आपके एक इंडक्टर होगा और एक कैपेसिटर होगा। इज इट क्लियर? तो ये हमारा टी सेक्शन है। The T section will look like this. Okay. Now we have to find out this value of this. The same procedure we can use it. That is, we will find out the characteristic impedance of the prototype model, and we will also find out the characteristic impedance of this, and then of this M derived filter by taking a ratio M. Then we will equate it, and ultimately we will get this is only C by M, C M, B by M, and this capacitor, this value will be 4M upon 1 minus M square C, while this will become L by M. तो देखिए बहुत चेंज आ गया थोड़ा सा। इज इट क्लियर? देखिए जब यहां सी होता है तो यहां पर एक इंडक्टर, यहां पर क्या होता है, इंडक्टर होता है, ठीक है, और यहां उसके साथ एक लग सकता है कैपेसिटर। जबकि हमारे लो पास फिल्टर में यहां क्या था, इंडक्टर था, ठीक है, तो यहां कैपेसिटर आता है और उस कैपेसिटर के साथ एक इंडक्टर आ जाता है। इज इट क्लियर? और उनकी वैल्यूज कैसे डिफर करती है ये मैं आपको पहले बता चुका हूं आपको। इज इट क्लियर? तो ये वैल्यूज आएगी आपकी जब आप कैरेक्टर इंपेडेंस को इक्वेट करेंगे, ठीक है। अब आप हम जो इसमें रेजोनेंस होगा, ठीक है, सीरीज रेजोनेंस होगा, हम उस सीरीज रेजोनेंस को वैल्यू फाइंड आउट कर देते हैं और उसको हम कहते हैं ये सीरीज रेजोनेंस विल प्रोड्यूस द frequency of infinite attenuation. So I will just place the value. Formula is very simple. Frequency of resonance is nothing but 1 upon 2 pi under root L C, ठीक है। तो यहां मैं L by M, L कितना है मेरा, L by M, और C कितना है 4M upon 1 minus M square C, ये वैल्यू मैं प्लेस करूंगा। देन आई विल गेट इनफाइनाइट फ्रीक्वेंसी ऑफ इनफाइनाइट एटेन्यूएशन एज अंडर रूट 1 minus M square upon 4 pi under root LC. Okay, now I also know that for a constant K prototype high pass filter, the cutoff frequency is given as 1 upon 4 pi under root LC. So I will just 1 upon 4 pi under root LC, इसको मैं लिख दूंगा fc, and therefore I will get this formula that the frequency of infinite attenuation is nothing but fc 1 minus m square. Okay, इसको फर्दर सिंप्लीफाई करूंगा मैं। इज इट क्लियर? तो फर्दर सिंप्लीफिकेशन से आपके ये रिजल्ट आएगा f infinite upon fc is equal to under root 1 minus m square. इज इट क्लियर? इसको चेंज करेंगे तो m is equal to under root 1 minus f infinite upon fc square, ठीक है। अब देखिए ये कैसे डिफरेंट है, लग रहा वैसे ही जैसे लो पास फिल्टर के लिए आया था, लेकिन एक स्लाइड चेंज है। वो स्लाइड चेंज में यहाँ पे लिख लेता हूं। वो क्या चेंज है कि जो लो पास फिल्टर में एम आया था, एम फॉर, आई एम राइटिंग फॉर लो पास फिल्टर, एम डिराइव लो पास फिल्टर, व्हाट वाज दैट एम? एम वाज नथिंग बट अंडर रूट 1 माइनस ब्रैकेट एफ सी अपॉन एफ इनफाइनाइट होल स्क्वायर। Okay. So this is what we have got for the low pass filter, but high pass filter, it looks something like this, but slight change is there, that it is not a ratio of fc upon f infinite, but it is a ratio of f infinite upon fc. So in case of high pass filter, the f infinite frequency should be lower than the, it should, now for example this is f, then and suppose in high pass filter, like this is the cutoff frequency, so it is chosen just below the fc frequency, is just below the frequency, while low pass filter it was above the cutoff frequency, but it is now below the cutoff frequency, so it will be like approximately near about it, but again the value will lie between 0 to 1 only. Is it clear? So let us now derive it. Okay, so how my variation of character impedance, attenuation constant and phase shift vary with the frequency, the same has been shown. The formula is very simple. Okay, here also that for between f infinity to fc cutoff frequency, the variation of the phase is like this. Okay, while for less than f infinity, the variation of like this is like this. Is it clear? Beta, in case of the pass band, it will be always be a 5, while in this case of the attenuation stop band, it will be like this. I can show you with the help of the so-called the diagram also, that how the character impedance variation is same as that of the prototype filter. However, the change is only observed in the so-called the attenuation. Now you can see that previously it was like this, but you can see that it was a very high value, near about the frequency of infinite attenuation. Okay, not we cannot say that it is a just sharp cutoff is there. No doubt it will take some time. It depends upon how you set the f infinity. Now if you will put this very close to this, then it will can have some sharp frequency. So it is very depend upon the design engineer how you put the frequency of infinite attenuation. If you put it here, then again you will not get a sharp cutoff uh, uh, attenuation. Okay, so what happens that the design engineer try to place not superimpose over fc, but try to place near about the cutoff frequency. This is the only work done to be by the so-called the design engineer for this high pass filter. Okay, now it is very clear that how the variation of beta is there with the frequency in the stop band. It is pi, then it is variation of with respect to the formula sine inverse in case of pass band. So I am leaving here only. Okay, so tomorrow what we will do that we will find out the we will do some numerical 2-3 numericals today for the high pass filter. Tomorrow we will do it, and we will come to know that once again only the first step is to find out the m ratio, just as we have found out in the low pass filter. Then we have to remember the prototype formulas for the high pass filter. Okay, what are the formulas for it? And then we have to find we have to just substitute the value of the corresponding c by m, or 1 minus m square upon 4m into cn, all this l by m, all this in t and pi section both. So today I have given you the diagram was somewhat misnomer. There was some mistake by me, so I will correct it and I will send you. Okay, and tomorrow we will do the some numerical. If any doubt यू कैन आस्क मी. अगर आपको किसी प्रकार की कोई समस्या है तो आप चैट बॉक्स में लिख सकते हैं. एनी प्रॉब्लम? No doubt. Then I think so the concept is clear to you that what we have done so far, that we have gone through the fundamentals of the M derived filter. Then we have focused on the so-called the low pass filter, and I have already told you that the formula will remain same, only slight change is there, and that slight change will be in the form of m. So first of all, in case of M derived filter, you have to find out the value of m. For a low pass filter, there's a formula is there. Then for the high pass filter, there's formula is there. Then with the help of that formula, with the help of that m, we will calculate the value of the L and C both. Okay, and then we will substitute in the corresponding T section and the pi section. Okay, so if concepts are clear, I think so there will be no problem. Otherwise, this whole chapter is based on formula. Okay, and if your concept is not clear, then it may happen that at time in during the examination that you mingle the formulas. Okay, so it is better that you should remember or the concept how to derive that given formula. Is it clear? So thank you. Okay, so we will meet once again tomorrow with some numericals related to the M derived filter. So best of luck to you for your preparation.